Next up, please welcome Brian Cruz, Head of Core AI at Samba TV. At Samba TV, Brian gets to use AI to enhance the TV viewing experience for everyone. He also leads the development of new AI models for the Edge and manages all steps of the model development lifecycle. Today, he's here to discuss how creating new AI-enabled products brings with it a number of challenges, one of which is the automation of the development process itself, and how, by combining time-tested best practices, we can automate many parts of the development process in order to build better products that go to market more quickly. Take it away, Brian.
Awesome. It's great to be a part of this wonderful MLOps Salon event. My name is Brian Cruz, and I'm the head of Core AI at Samba TV, where I get to use AI to enhance the TV viewing experience for everyone. I'd like to speak with you all today about a topic very dear to me, and that is automating AI development for the edge. Now, the ability to run AI algorithms closer to end users provides a number of benefits, not just limited to better latency, privacy, and cost. In fact, the advent of edge computing has initiated a new paradigm for distributed computing that enables an entirely new class of products and solutions. Creating new AI-enabled products within this new ecosystem brings with it a number of challenges, one of which is the automation of the development process itself. And this is precisely what I wish to speak about today in the context of the MLOps movement taking place today. So first, let me tell you about my background. So again, I'm the head of Core AI at Samba TV. I lead efforts to, as I like to say, put the AI in entertainment. I work with data scientists, machine learning engineers, data engineers, embedded engineers, and DevOps experts in order to improve TV viewing and recommendations by putting AI on TVs. Samba TV's mission is to create data at the heart of TV, powering a more scientific approach to advertising and a better viewing experience for everyone. Recently, I also worked with Udacity as a course lead for the free Artificial Intelligence of Things course, based on the AIoT playbook, which itself will soon be available from Springer. Please check it out. And before that, I worked at Salesforce as machine learning engineer for Einstein Guidance, the sales forecasting tool used internally by the executive team. So enough about me. Let's take a look at what we're going to discuss today. So we've got 4 parts here. First, introduction to Edge AI. Secondly, the artificial intelligence of things. Third, automating AI development for AIoT. And lastly, we'll cap it off with a summary. Sound good? Let's get started. Section 1, Introduction to Edge AI. The purpose of this section is to define what edge computing is and to make the case that not only is it immensely useful, but it is also pretty challenging to get working. So let's take a look. What is Edge AI? Well, Edge AI, or more generally, edge computing, is artificial intelligence that is run closer to devices and users, that is, to the sources of data. The opposite of edge computing would be cloud computing. And while the public cloud has transformed so many aspects of our lives, there's still certain things for which the cloud isn't ideal, especially when it comes to latency and reliability of your connection to the internet. Here are some examples. Smart household devices, such as a smart vacuum, a connected device that automatically cleans your floor using AI. Now, it'd be a bummer if your vacuum stopped working because it goes into a Wi-Fi dead spot in your home, or even worse, because the server's DNS is misconfigured. Secondly, we've got connected cars, the quintessential example being the Tesla. So modern cars use edge intelligence to avoid accidents and even set the windshield wiper speed based on video from a camera pointed at the windshield. A super interesting example, I think, is a Large Hadron Collider at CERN. The LHC generates 600 million particle collisions per second. Multiply that by the more than 1 million sensors, and you have more data than you could ever store. A multi-tier system that uses FPGAs to compress the sensor data, more than 1,500 servers to go through this data to determine whether the recorded events are useful. And then, finally, after all that, this data is stored and distributed. Lastly, we have the cell tower, and we have what are called multi-access edge computing, or MEC. As we'll discuss more, Later, the edge doesn't have to be in the same building as a device in question. In fact, edge data centers can be located at cell towers themselves, or even slightly upstream, for instance, at the telecom central office. 5G mobile technology has high bandwidth, and coupled with edge computing, it instantly gives every device low latency access to a computational powerhouse if the supporting hardware is deployed and the software knows how to use it. So edge computing seems interesting and is actually already all around us. So what sort of prospects do we see for its growth? Well, let's take a look. Here we have the years from 2016 to 2021. The green line on the top peaks out at 85 zettabytes. Now that's 21 zeros. It shows the amount of usable data created per year and is rapidly increasing. The blue line at the bottom shows the amount of data center traffic per year. We see that the cloud's growth isn't able to keep up with the data we're creating from, for example, the multitude of sensors we have. And so the gap between the two shows the potential for edge computing. Now, if you look at the diagram, it says fog computing, and that's a term that refers to any of the multiple steps between the devices, so things, and the core data centers and clouds. We see that most data is not even being sent to data centers. Ironically, traditional big data, that is data in data warehouses, data lakes, data swamps, is relatively small. If we are to realize the potential in this data at the edge, we must expand the notion of big data to include edge storage, edge computing, and edge intelligence. Now, let's take a look at some of the benefits, drawbacks, and challenges to working with the edge. Okay, so potential benefits. We have lower latency. 5G is a key example here. Single digit millisecond latency is claimed and might be possible, but 10 to 20 milliseconds seems to be more the norm. Less bandwidth usage. Essentially, this means as much data as the edge can handle can be transmitted and processed. So imagine attending a Formula One race and being able to follow the race from different in car, trackside, and airborne camera perspectives, all delivered in real time. Multi access edge computing made this possible even before 5G, as mentioned in a blog post on the ETSI website. ETSI being the standards organization behind MEC. We also have higher reliability. So consider a factory that uses the cloud for maintaining its operations in real time versus using an on-prem edge data center. So the on-prem edge data center will be there and is more reliable than the cloud. So also better preservation of privacy. This is a big issue. Customers need to be able to control their data as a fundamental right. We can enable AI use cases to provide value to customers by processing the data on the edge and even on device. And we have reduced costs. Processing data closer to its source can mean reduced costs. Simple enough. Uh, Increased scalability. The edge can literally be in any building or cell phone tower. So that's a lot more scalable than the numerous but smaller amount of data centers there are in the world. So drawbacks? Drawbacks of the edge are there are more attack vectors, more devices, more servers, more entry points, etc. means more potential vulnerability. And if we're talking about processing on the device itself, there's pretty limited processing power. So low power devices are not really. You can't put a GPU, for instance, or very powerful GPU on some of these smaller devices. So limited processing power. This is true, especially for low power devices. However, significant strides are being made to move more computational power closer to the users. This is true not only for devices, but also on prem edge nodes as well as network edge nodes. So, the challenges we have here uh, one of the big challenges is that AIoT or Edge AI incorporates hardware, software, and AI. The development of hardware, software, and AI are pretty different and they come with their own requirements. So, for instance, if you're a software company working on a new robot vacuum, you'll want to make the sourcing decision regarding hardware components such as sensors earlier in the process and lock it in place. So it's something you can't change, especially after the start of production. We also have organizational scalability. Often the work here will involve many different teams needing to work in coordination. So being able to work iteratively requires a more mature organization that can handle the synchronization of these teams. Another aspect is custom embedded software and hardware. So generally, the edge is more heterogeneous and involves more low-level languages in the cloud. This is especially true on devices. And last one in this list is first time right. Hardware is more difficult to update than software, and in many cases, it's just impossible. Also, if you do have over the air updates, OTA, it's less trivial than updates to cloud microservices. So many times when working with the edge, it's imperative to get things done right the first time. Cool. So moving on. You may recognize these boxes from Google's 2015 paper on technical debt in machine learning systems. And so here we have in this meme, the first one of all these boxes. So very little of production machine learning systems is actual machine learning code. That's what these boxes communicate. And many successful MLOps operations have multiple systems. So how many of them do you want to be manual and how many of them do you want to be automated? So at the top, we have none of this is automated. And the bottom, we have all of this is automated. So obviously, it's nicer to have more of these things automated and to have less headaches and to actually be able to create a product that you're able to make better over time. And so the case for Edge AI is even more extreme than this. We can add boxes for OTA updates, test labs for real devices, and much, much more. So let's dive into the complicated world of AIoT. Section 2. The artificial intelligence of things. So AIoT is a portmanteau of artificial intelligence and also the Internet of Things. As I like to say, behind every smart device, there's a cloud. So let's take a look at this. First things first, like everything else, AIoT offerings can come in the form of products, services, or even a hybrid of the two. When most people think of AIoT, they usually think of things like smart speakers or robot vacuums, and these are products and they're great. Now, there are also AIoT enabled solutions, which basically means using AIoT to solve a specific business problem. So, for instance, a factory may acquire a solution that retrofits their machines with sensors using AI for predictive maintenance. So, being able to fix the machines, they could be machines for making widgets or even escalators, things like that, fixing them before they break. So, in the example here, a company has productized a solution for inspecting building facades using automated drones. Now, we see that the images of the building facades use cloud intelligence, while the actual flying uses edge intelligence. After the zone zips around the building, scanning all the walls, and after the cloud data pipelines find cracks and corrosion, a facade report is sent out. And that's what we have here. This example actually comes from the AIoT playbook. Let's take a look at another part from the playbook. So when developing AIoT products, there's a notion of the product launch or start of production. After the start of production, you can easily update your cloud systems. And if you are able to send OTA updates to your devices, then you can even update the models you're using, usually keeping the general AI approach stable. What you cannot do is update the sensors on your device. And in fact, the sourcing process for such sensors and components in your device is something that needs to be frozen earlier in the development process. What the AIoT playbook suggests is that after the initial requirements, use cases, KPIs, etc., are defined, uh, an attempt needs to be made to balance the hardware, software, and AI so called magic triangle to make a prototype that actually provides value to a user. So after you have the prototype that is that 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 works, important components of the hardware can be frozen earlier in the process. Then after that, the overall system architecture, including the software on the edge, on the cloud, as well as the OTA process, those can be frozen. And that allows a stable platform for the development of AI and the iteration of AI. Lastly, using that platform, the MVP version of the AI model can be developed and released. So the main parts that the IoT part of AIoT adds are the hardware part of this and also all of the edge software and edge cloud communication. And let's take a closer look at edge. So this was mentioned earlier, but it requires a specific callout. There's more than one edge. Remember, the edge just means close to the source of data. The Linux Foundation categorizes edge into 3 parts. So there's the edge device, usually has lower power requirements. There's also an edge node that is in the same physical location as a device. So that could be a hub, or it could even be a beefy computer. Finally, there's the edge, which is not the cloud and not on premises. And this is sometimes referred to as a network edge. This includes, for instance, the MEC data centers run on the telecommunications side of things for 5G. In addition to there being more than one edge, it's not just cloud intelligence and edge intelligence. It's not just you do everything in the cloud and then, or you do everything on the edge. There's everything in between. So sometimes you can call it hybrid intelligence or even co-inference. So another aspect to this is, or another thing to consider is not just the inference, but where the training of the models takes place. So this pyramid on the right summarizes the possibilities into 6 levels of edge intelligence. So it's not just one type of edge intelligence. So if we start at level 1, there's at the bottom near the fully cloud intelligence. You have level 1, the first level of edge intelligence. This is cloud edge co-inference. So that means part of the algorithm is on the edge and part of the algorithm is in the cloud, with training taking place completely in the cloud. If you go up in levels, you can get to what most people consider to be edge AI, and this is level 3. So that means inference happens on a device, on an edge device, though the training of the model. So, for instance, transfer learning of a computer vision model, this still happens in the cloud, and it's distributed to the device. Lastly, if you go to the very top, you have level 6. And in level 6, both training and inference take place completely on the device itself. So this is sort of like the ultimate level of edge where very little data needs to be sent to the cloud. Training happens on the edge device as well as inference happens on the edge device. So now that we have a handle on some of the complications or aspects of AIoT, let's finally dive into it. Section 3. So automating AI development for AIoT. So how do we automate hardware/software systems? Here we'll look at an important example from the airline industry and also take a peek at what Samba TV does to test the TVs we work on. So let's get started. Now, first, I'd like to address existing MLOps tooling. It's been an incredible couple of years for MLOps. There are many new tools and startups, and while at times it's confusing, it's also pretty exciting. So the list on the right is a Google sheet maintained by Chip Huyen, which has 285 of these tools and startups and counting. So they're built, these tools and startups, they take some of the best principles from DevOps and some of the best principles from data ops, and they put them together and they add their own sauce on top of it. So we have a lot of really cool things coming out today. So in order to get real value out of your models, you really no longer need to roll your own AI platform in many of the popular use cases. So that said, in order to deal with the development of hardware, eventually you'll need to work with real hardware. So that brings me to one of my favorite uh, types of simulations, and that is the Iron Bird. So the Iron Bird, which is used for testing airplanes, put simply, it's the guts of an airplane, actuators and all, installed in an easy to access arrangement, such as pictured here at the top left. So in the Iron Bird, the aerodynamic surfaces of the plane, so that's the flaps and the rudder and that kind of stuff, they're all still there. And to mimic the properties of air flowing over them, you actually have other hydraulic actuators connected to a computer running aerodynamic simulations, and they're providing a load on these flaps. And they're actually pushing them if the air pushes on them. So an Iron Bird can also be equipped with a real cockpit and a flight simulator so that pilots can fly complete missions from the ground, and the Iron Bird just moves its flaps the whole time. This allows many batteries of tests to be run long before the real aircraft is even produced, increasing the speed to market. And also, in this case, it's much, much safer than flying a real plane to test it out. When I first learned about the Iron Bird, I thought it was a pinnacle of coolness of simulation. So, since people like putting pyramids into talks, I decided to make a pyramid for the different levels of simulation for testing in AIoT. At the bottom, we have testing and production, which we've all done before. Um, and it's only a simulation if we're not in a simulation, or if we are in a simulation. Just kidding. So these are models and devices acting with the real world with real users. And I would put A/B testing into this part of the pyramid. Um, Next up is model in the loop. This is what we're used to when we're testing ML models. We test the model against a test set and see how well it's performing. But you don't have the software around it. You don't have the hardware around it. It's just a model by itself. Next, we have software in the loop. The model will be called by some component of software. So when you have your software libraries and they go into production, you want to make sure they work. So you're going to run a software in the loop simulation, which takes one of these components, or if you're integrating multiple components, takes them all together and runs a virtual simulation of them all at the same time. And it's simulating the hardware. So you have no hardware in here either. Um, One level up, we have hardware in the loop. So you send real hardware devices signals so that it thinks it's in a real environment. So for instance, you can test the ECU of a car using a simulated motor, or even the Iron Bird example itself falls here. Lastly, in the test lab, you put your device to the real test in a real environment and sometimes with real users. Testing a new kitchen appliance, build a kitchen and have someone use it. It is perhaps the hardest to do, but it's the best way to validate that your product is actually providing value. So I'd like to take a look at what we built at Samba TV. And here we have Samba TV's television labs. We have a number of television labs all around the world, which we use to contribute to the scientific understanding of TV viewing. And we support these different levels of simulation within our labs. So, we actually have some TVs hooked up to production. We we run models not on TV sometimes. Sometimes we run them on the TV, or sometimes we run the models in the software that's supposed to go on the TV, but not actually in the TV. And and the hardware devices, when we do a hardware in the loop test, we actually have the devices wired up. We have IR blasters for changing the channels like a real human would, and we are able to turn on and turn off our TVs remotely. This is something that was sort of forced by working remote. We needed to be able to reset our televisions from our homes. So one of the cool things here is that we've automated true set building, experiments, and also benchmarking of our algorithms in production, as well as algorithms that we're experimenting with. So that's about it. Um, that's a quick look at AIoT and development for AIoT. So let's look at the summary here. So to summarize, we have these three main points. Edge intelligence will grow by leaps and bounds in coming years, allowing the development of new technologies based on AI's application to low latency use cases. Another point is that the development for AIoT systems is especially difficult since they combine hardware, software, and AI. Additionally, how computation and data can be distributed is a complex problem. Lastly, by combining best practices from each of these three areas, we can automate many aspects of the development process in order to build better products that go to market more quickly. So excellent. Thank you for listening to my talk today. I look forward to hearing your questions.